Okay, so this is 1. This is 1/12. Okay, this is 1/2 of 1/12. This one is 1 over 12 squared, or 1 over 144, or 2 over 288. So this one's 2 over 288. This is 1/2 of 1 over 144, or 1 over 288. So these two together are 3 over 288. Okay, now if this is 1 over 288, then this is 1/2 of 1 over 288. And this is 1/3 of 1/2 of 1 over 288, because this is 1/3 of that. So then if you combine these, you get 1/2, because 1/2 is in both of them, times 1 plus 1/3 times 1 over 288. And 1 plus 1/3, 1 and 1/3 is 4/3. And 1/2 times 4/3 is 2/3. So you get 2/3 times 1 over 288. And this one down here is in the noise. So we're going to not worry about that. And let's look back at what Frantius said you get. You get 1 and 1/2 twelfths. So 1 and 1/2 twelfths. So this is 1 and 1/2 twelfths. Plus 3 over 288. This is the 3 over 288. And then this is the 2/3 of 1 over 288. So basically you're getting 3 digits of base 12 plus a unit digit. So 4 digits of precision there. In our calculation, we used basically 4 base 12 digits, and the Roman hand abacus has only 2. So this calculation could not have been done on the Roman hand abacus. It must have been done on a counting board similar to the one we used. Please note that this proposed Roman counting board abacus is an exact duplicate of the Salamis tablet. That is, the lower grid has 11 lines. The upper I've truncated because of paper restrictions, but also probably wouldn't use more than 2 lines for exponent in most applications. So it looks to me like the Romans directly mapped their counting board on this. If you look at the right side of this counting board abacus, it's a duplicate, almost an identical duplicate of the Roman hand abacus. The powers of 10 go from 0 to 6, and you have 2 digits for base 12. So the problem is to square 265. For that purpose, the Romans would use their counting board in decimal mode, and so we're going to be using this. Now, I'm not going to try to register it against the Roman numerals here. What I'm going to do is to start like we have before with the number 265, 250, 65, starting in the first digit here. And now since I have an implied decimal point here, what I'm going to do is count back 1, 2, 3, and put 3 here for my radix point shift. So 3 is 5 minus 2. Okay, now we want to multiply this by itself, so we're just going to duplicate this here. Okay, now we need our exponent. We're going to add the exponent terms together. So we have this and this. and then this and this. Okay, this is 4, which is 5 minus 1, I'm sorry, 5 minus 1. And these would cancel. So we're left with 6. Okay, so let's see. We could start by doing 2 copies here. So I'll do 1 copy and then double it. Okay, now I'm going to double it. So this is 2 becomes 4. This is 5 becomes 10. I need 2 here, and this comes up here. Okay, these cancel. This is 3. And so I've done the 2. Can do this guy. Let's register this. Okay. So I need to copy to here. Is that right? Yes. Okay. So we've done that. Let's register this. And these cancel. Okay, now I need to double this number. So if I double this number, it goes here, and halve this number. This is 5 becomes 2 and a half. Half of this, and then 2 and a half, which promotes, and then half of that. And this is 3. Okay, so I want 1 here. So I start here, 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 and here. Checking. Let's see. Okay. So let's collapse that. Promote this. This is 4, which is 5 minus 1. Promote these. These 2 cancel. Promote. Okay, that's that. Now we need to do this one. And here, and here, to here, to here, and then. Okay. So I'm going to read the answer, so why don't I just bring it into the center. This is 3, so that's 5 minus 2, and those cancel. These cancel. So now let's figure out where the decimal point is. This is 6, so it's 1, 2, 3, 4, 5, 6. Decimal point is right here. And actually it turns out that's convenient because that's where the unit is on these letters. So we could actually read this as a Roman numeral. But let's see, this is 7, 0, 2, 2, 5, which is correct.